Hello, in this video I'm going to look at the trigonometric substitution method. So basically whenever you see an integral that may contain one of these three forms, there's a type of substitution that needs to be made. So for example, if you have the first one, basically you have that you're going to take a times sine of theta, and that's going to equal to u. Now in any case, you can make the substitution by differentiating, where you would have a cosine of theta d theta is equal to du. Now what you would have to do essentially is actually substitute this u into this equation, which then gives you the square root of a squared minus a squared, and then you have sine squared theta. Now, in this case, what happens is that you end up with an a, but you also end up with the square root of 1 minus sine squared theta. Now, using the identity that cosine squared theta plus sine squared theta is equal to 1, you can actually say that this is equal to cosine squared. What that means is that you're ending up taking the square root of cosine squared. So in that sense, you have that that is equal to cosine of theta. Now, that actually tells you, yes, that a cosine theta is equal to a squared minus u squared raised to the 1/2. But another way that you can do it, which is a very common method, is where you would make a right triangle, and you would basically label each of these respectively. So like for example, you have that by definition the opposite is u and the hypotenuse is a. But Pythagorean theorem says that basically a squared minus u squared is going to be this adjacent side. Why? Because you have that the value of theta is right here. So in that case, by using the adjacent and the hypotenuse, that's where basically you would say that cosine of theta is equal to the square root of a squared minus u squared, and that's all divided by a. Of course, you're just multiplying by a on both sides. Now, if you have the third case, though, basically that tells you that you have to use tangent. So if we were going to use the third case, and I'll just kind of write it down over here, the third case says that, not third case, but the second case, sorry. The second case says that you have that a tangent of theta is equal to u. Now in that case, that's a lot easier because you know that if you differentiate this, you're going to get a secant squared theta d theta is equal to du. But similarly, if you use a right triangle, you're basically going to find that a secant of theta is equal to the square root of u squared plus a squared. Now in this case, we use u's just to account for chain rule, for example. Now, if we have the last case though, basically the last case states that you have to use, so let's just draw like a white line through here. Okay, and then we'll just draw a line right here. Now, looking at the last case where you have the difference of the two squares, so we have that that's going to be, okay, so we have the square root of a squared minus u squared. Actually, it's the other way around, isn't it? Okay, so that's going to be u squared minus a squared. So by definition, we have to say that a is equal to secant of theta, and that's equal to u. Now, of course, if we were going to use our triangle, we would just have to be careful with respect to the signs, essentially, because of the definition of the secant function. But in either case, like, it always kind of works out that you can use the direct substitution in any case. Now, how we can see that is perhaps like in an example. So let's say that we look at an example of which takes, okay, so let's say that we have 1 divided by x, and then we have the square root of x squared plus 1, and then this is dx, and then we're integrating this. Okay, so basically we see that this is of the form a squared plus u squared, which means that basically you're going to use that tangent of theta is equal to our u, or x in this case. So what that means is that we differentiate this where we get secant squared theta d theta is equal to dx. Now, in any case, for example, notice that basically you are going to substitute x with tangent squared, and then you'll notice that it's secant squared. Okay. But we mentioned that basically we can use, as always, a right triangle to figure out, like the relationship with respect to the angle theta. So we have that the opposite is x and the adjacent is 1, but using Pythagorean theorem, we have that that's x squared plus 1. So in any case, we're just going to basically say that x squared plus 1 is equal to secant of theta. So that's what we'll substitute there. Now notice that when you substitute into the integral, you're basically going to get that that's going to be 1 divided by tangent of, tangent of theta. Okay, but we multiply this by secant theta, but notice that the dx is secant squared theta d theta. Now, in any case, we can see that essentially this is going to be equal to the integral of, secant, because you have that one of these cancels out, the secant and the power. So it's going to be secant of theta divided by tangent of theta. And this is d theta, by the way. So in this sense, we have this integral that we need to solve. Okay, but note that, for example, that we can actually work out what secant of theta over tangent of theta is equal to, because we know that it's 1 over cosine of theta, and this is divided by sine theta over cosine theta. But if you basically reduce that, you're going to get that the cosines actually cancel out, which that leaves you with 1 over sine, which is equal to cosecant of theta. So in that case, we just need to integrate cosecant of theta. Now, basically, from there, we know that we just need to say that, okay, well, we have that we're integrating cosecant. So let's go ahead and rewrite our integral because we've reduced it down to cosecant of theta d theta. Okay, but we have that this is actually a known integral in either case. This is going to be equal to negative natural log of cosecant of theta plus cotangent of theta, and then it's going to be plus c. Now, notice that by definition, we can input whatever cosecant was with respect to our diagram. So cosecant would be hypotenuse over opposite, and cotangent would be basically the adjacent over the opposite. So let's rewrite this using the definition. So that's going to be the negative natural log of, okay, so looking back at the triangle, you should get x squared plus 1 divided by x, and then plus 1 over x. And then we'll just do plus c. Now, in any case, you can actually rewrite this because, for instance, they have the same denominator, and you have a negative 1 there. So basically, that's going to give you ln of x divided by the square root of x squared plus 1. And then you have plus 1, and then you just close it, and you have plus c. So this would be the derivative, or antiderivative, of the of this integral right here. Now keep in mind that this actually represents also the integrals that involve hyperbolic functions. So that's one thing to consider, is that your answer is going to be very similar to a hyperbolic function. Now you can actually check your work essentially, because notice that notice that this is actually equal to the natural log of the absolute value of x minus the natural log of the absolute value of x squared plus 1, and then you have plus c. So it would probably be easier to differentiate this function and then compare the results and see if that gives you back the exact same integrand function in either case. Now, let's say that we're looking at a different integral, and let's say that it's of the form where you have x squared divided by the square root of 9 minus x squared, and then it's dx. Now, what we need to do is figure out what the a is. Now notice that the a is basically 3 squared minus x squared, and that's going to help us determine the equivalence, or the substitution. So we have 3 sine theta equals to u. Well, actually in this case it's going to be x. So 3 cosine theta d theta equals to dx. But then I know that if I square this, I'm going to get 9 cosine squared theta equals to x squared. I'm just taking care of this part right there. So it looks like actually we're going to have like 27 cosine cubed, but we'll see what we get. Now, furthermore, we just need to go ahead and use our triangle as needed, if it's needed, which it's no problem. We can say that the opposite is x and the hypotenuse is 3, which means that we have the adjacent side is 9 minus x squared. That's where it tells us that 3 cosine theta equals to the square root of x squared minus, actually it's 9 minus x squared. Okay, so we'll go ahead and plug in everything into this equation, or integral. Okay, so we have the top part is going to be 3. Actually, this should be sine squared, right? Yeah. Okay. That didn't turn out well, but it's okay. So we have that that's going to be 9 sine squared theta equals to x squared. Okay. Now, in this case, that's going to give us 9 sine squared theta divided by, well, we said that this is going to be 3 cosine theta. But what is dx? Dx is actually going to be 3 cosine theta d theta. Now notice that basically the 3 cosine thetas cancels out, and you're left with 9 sine squared theta. So in any case, that means that the integral is now reduced to the integral of sine squared theta d theta. But what does that mean? That means that we have to reduce it basically as 1. Let's do this. Let's do minus, 1 minus cosine 2 theta all over 2. And then this will be d theta, right? Okay. Now, from there, we just need to integrate. So we have 9 halves times, well, this is going to be theta minus 1/4. Now, it's 1/4 because you have a 2 and then a 2, so it's minus 1/4. And then you have sine of 2 theta, and then it's going to be plus c. Now, we can go ahead and, for example, distribute, but I would recommend that you go ahead and you substitute the theta as sine inverse of x over 3. That's just because of the fact that if you go back to over here, you have that sine theta equals to x over 3. Now, notice that this is also going to be minus 1/2 because you're going to expand sine 2 theta, which you get 2 sine theta cosine theta, but the 2's cancels out and gives you 1/2. So you have sine theta cosine theta plus c. Unfortunately, I need one more substitution. Hang on. Yeah, if we were gonna take out the 2, that would be a 1/2 then in that case. So let me go ahead and put that instead as 1/2. Okay. But then when I expand it, that technically cancels that out to be just minus sine theta cosine theta. Okay. So now we go ahead and we plug in everything with respect to what we have. So this is going to be equal to 9 halves times sine inverse of x over 3 multiplied by, so sine of theta is going to be x over 3, so we have minus x over 3, and it's multiplied by also the square root of 9 minus x squared all over 3, and this is going to be plus c. So distributing, basically you're going to get that this is equal to 9 halves sine inverse of x over 3 minus, okay, so the 9 is going to cancel out essentially, so you just have 1/2, then you have x, and then you have the square root of 9 minus x squared, and then that's going to be plus c. So this represents the solution to the integral of x squared over 9 over x squared over the square root of 9 minus x squared. Now, of course, if you differentiate the answer, it's going to give us back the same thing as mentioned. So in any case, like if you go back and you see that your differentiation doesn't give you the integrand function, then we know that there's an error somewhere. It is also possible to do this problem via probably like a formula, or in fact maybe we can probably just use integration by parts, for example, because notice that in any case that you could probably use integration by parts and figure out like what that's going to be equal to. But that makes it more challenging in either case, like if you were to kind of break this up into UDV or something like that. So the other one of which that we can look at is an example of which looks at when you have a difference of squares. So we looked at the difference of squares with respect to the inverse sine function, but now we'll look at the cosecant. So, or not cosecant, but secant. So here we have the integral of, okay, so we have 1 divided by the square root of x squared minus 16. Now here, basically you have that the a is 4, so I know that I'm going to have 4, and I'm going to put secant of theta equals to x. Now, in any case, for example, I know that this is going to be secant squared minus 1, which is just tangent. So in either case, I already kind of know that 4 tangent is equal to x squared minus 16. Now, if you want to basically make a triangle, you actually could use a triangle, which would just tell you that, okay, well, the hypotenuse is x, the adjacent is 4, and then using Pythagorean theorem, x squared minus 16 will be the opposite side. This would be your theta. Now in that case, let's put a dx right there. In this case, like if you differentiate this function, you'll get that basically that the dx, let's squeeze it in over here, is equal to 4 secant theta tangent theta. Okay, so that means that the integral is going to be 1 divided by 4 tangent theta multiplied by secant theta tangent theta d theta, and we have a 4 there, right? Okay, so notice that the 4 tangent thetas basically cancel out, and it leaves you with the integral of secant of theta d theta. Now, that's kind of interesting because basically that gives you that that's going to be the natural log of the integral of secant of theta plus tangent theta and then plus c. So here, you know, we kind of have that our answer is with respect to theta. So here we have the natural log of x over 4 plus, okay, so that's going to be the square root of x squared minus 16, but it's going to be divided by 4 because it's TOA, so we have that that's going to be opposite over adjacent, so that's going to be over 4, and that's going to be plus c. Now, technically the answer can be rewritten in another way, of which in this case it's just going to be the natural log of x plus the square root of x squared minus 16 and then just plus c. The question is why though? Well, if you kind of look at how you have, you know, like ln of a over b is equal to the ln of a minus ln of b, this denominator right here, the 4 and the 4 here, means that essentially our last portion is going to say ln of 4 plus c. But this right here is also a constant. So in either case, the solution is also, you know, the ln of x plus the square root of x, square root of x squared minus 16 and then plus c. Technically, all of this will be positive though in either case. So I always get this question about whether, you know, we can mix the different techniques that we've already learned within this course, and by then, you know, we're 8 weeks in. So, you know, one typical question might be, for example, like if you have that you want to find the area, or the, you want to find the volume. And in this case, like if you have y equals to, let's say like 4 divided by x squared plus 4, and then you're looking at it from 0 to 2, and then, you know, you might say that it's with respect to the x-axis. So in either case, like if you were gonna, you know, try to find the volume of a solid with respect to this equation that's given, that means that basically you're just using that r of x is equal to the function 4 over x squared plus 4. And basically you're using kind of like that the area is approximately pi times r of x squared, which in this case would be 16 pi. Okay, so it'd be 16 pi over x squared plus 4 to the second power, essentially. So in any case, like, that would be an integral from 0 to 2 of 16 pi divided by x squared plus 4 to the second power, and then that would be dx. Now, of course, the constant 16 pi can be removed, and you have that it's just times the integral of 1 over x squared plus 4 to the second power. Let me get rid of that. And then you have that it's going to be dx. Okay, so once you get up to this point, then it's just a matter of, like, how do you integrate this equation in either case? Like, because you have x squared plus 4. Now, I would say, it may be best to go ahead and try to work it out on your own to where you see, like, can you figure out what is the integral of this equation? Now, I'll give you that the area approximately will be 4.04. Okay, so yeah, so this will be approximately 4.04. Okay, so it'll be interesting, like, if you can figure out how to get this area, or volume actually, right? It's actually volume. How to get this volume. And note that, like, if you were to graph this in the x and y plane, basically it's kind of like where you have a curve that's odd. So it kind of goes like that a little. And then you have that it's only going to go up to 2. So in any case, like, you have that this is the area of region. And we know that we're going to rotate it with respect to the x-axis. So we're going to rotate it. And then we generate our solid, of which accordingly you'll get that the area is 4.04 approximately. Not area, I keep saying area, I'm sorry, but the volume. Yeah. Now, there is probably not any other way that we can do this problem because of the fact that it's with respect to the x-axis in either case. Because if you try to rewrite it with respect to y, that's actually going to be very complicated, most likely. So it probably would not be the best idea to do something like that, because yeah, you kind of have no choice essentially. But if you wanted to find a solid that was generated with respect to the y-axis, that would be a different solid, but it would be an interesting problem, because now you could probably then use the shell method, because then you would have that the radius of the cylindrical shell would be x, and then the height would be given by this equation right here. But then it would be multiplied by 2 pi in either case. But note that it may not require actually using trigonometric substitution in actuality, because once you formulate that integral, you'll notice that it's times x, so 4x, which in this case means that you could use a simple u sub. Okay, so in any case, we have that we can create problems of which that wind up using different methods that you have learned since, basically kind of like Cal 1 and also some of Cal 2 so far.